Welcome to my title, Converging PCIe and TSN Ethernet for Composable Infrastructure in High-Performance In-Vehicle Networks or Embedded Systems. I'm kind of the odd guy to the Storage Developers Conference because I'm not a storage developer. I develop with storage. And what we're basically, mouse focus, what we'll basically do is we're integrators for what we call high-performance embedded systems, and most of these systems have some form of packets, whether it's a video frame or a pixel or network packet. We use these unconventional architectures, sometimes called domain-specific architectures, for accelerating systems. And most of these systems that we're dealing with today have some flavor of PCI Express and or CXL for cache coherency. We use a lot of Ethernet and protocols on top of that, TCP/IP, TSN. I'll shed some light on TSN because apparently it's not well known in this kind of a community. And again, audio-video standards, and sometimes we transport one over the other and vice versa. And we're working basically in an ecosystem with German Fraunhofer. German Fraunhofer is basically Caltech on steroids. By now they're like 25,000 researchers and PhDs and professors, and about 3,000 bureaucrats. And that allows us to tap into very special experts and quickly can tap into hundreds of those experts for all kinds of specialty that we need to implement or where we're looking for solutions. And because the Fraunhofer Charter is basically paid for applicable and useful research, they're not allowed to sell products. They look at partners like Missing Link Electronics to commercialize those products, support those products via licensing schemes and via engineers who can fly across the planet in order to do some maintenance and or some debugging. And the other partner we're working with is Elemaster. Elemaster is a worldwide manufacturing group because more and more our customers are looking at us for turnkey solutions, which is hardware and software in all kinds of odd shapes. And Elemaster basically gives us a worldwide presence for manufacturing as well as for servicing parts across the planet. So what I'm talking about today is a problem which is really growing up in these classical automotive OEMs, Ford, GM, BMW, Volkswagen, you name it. Not so much the new ones who basically are greenfield car makers, right? Tesla is one of them. And the problem has to do with the cable harness, the wiring harness. If you're in an industry where one piece that you have to buy from a vendor becomes the second most or sometimes the most expensive component in your product, okay? For Volkswagen, that's public numbers, the wire harness for the Volkswagen Golf 8 is becoming the second most component right after engine and transmission, which Volkswagen manufacturers designs themselves, okay? And if the vendor is not making any money on that product, you know you're facing a significant problem, right? This is the most expensive component, but the vendor who builds these wire harnesses is making a fortune. Then it's a stable ecosystem, but it's not, okay? That's why the world has to change, and it basically looks like this. This is about an 8 or 9 year old picture of a wire harness which is built out, and the cost behind it is all manual labor. Because most of these cars on the road today, the wire harness is custom made, and which is expensive to manufacture, and it's custom manual labor to putting a wire harness into the car. Okay, so that's why the automotive industry has been switching over to different architectures, which are called zone-based architectures, and zones are basically not split over functional domains, but over physical areas. Physical proximity and location matter much, much more than the functionality behind. And it has to do with getting the costs down and sharing things, right? So if you look at a modern computer, we are used to backbones, okay? So the car industry is facing the same challenges by changing from a functionality-driven connectivity over to a physical or basically proximity-driven connection. And that means we have a ton of data aggregation and a ton of data pre-processing in what we call these zone controllers, the blue boxes around here, right? And that means, well, all of a sudden we're talking high bandwidth connectivity standards, and we basically need to talk about a high performance compute within the car, right? So from these 99 different control units, electronic control units or ECUs in car speak, we're migrating over to something which is less than 10 of those units. And one of those examples, just to visualize things, is the idea of a smart corner where you integrate the headlight along with LiDAR, radar, other sensors in order to make automated driving more doable or in order to provide more safety driver assist systems. That's the idea, and that's the main force pushing for new standards and new applications in there. And one of the things that we see is there's a huge push in those new automotive networks for standards from other industries. And in this case, we're looking at PCI Express / NVMe Express because it's pretty much driven by cost per performance. If you buy flash drives these days, most of them have some form of an NVMe and a PCI Express connector anyhow. And because of the sheer volume that these big hyperscalers are buying, the car industry has no luxury of defining their own flash access standard or flash connectivity standard. Okay, and the other key driver is driven by compliance. The challenge of delivering functional safety, proper functionality, which is standards like ISO 26262 or security standards or the safety of the intended functionality standards, right, are so challenging for delivering a full system that you really have no bandwidth to invent a new standard. So the pressure is on borrowing standards from other industries like PCI Express, NVMe Express, Ethernet, and so forth in order to build these next generation modern systems. So our motive and missing link electronics is proudly sourced elsewhere. So we look at all kinds of industries and try to look at themes and ideas and concepts which are either mature or brand new and crazy, and see whether we can apply them to our customers in the embedded business. And in this particular case, it's kind of a bi-directional street here. So the first thing is, let's look at what data center and these next generation cars may have in common, okay, and what they may not have in common. And when we look at this, the longevity is about the same. It's 10 to 15 years that a car needs to drive on the road, and while most hyperscalers say that they retooling things every 2 years along with a new thing, we see that we have old bare iron in AWS EC2 systems, and they need to run, right? So longevity is quite similar. What is called in data center high availability, typically driven by service level agreements in the car industry, we call functional safety, right? And it's actually the opposite side around. So instead of looking how to build high availability and edit after the fact, kind of what was going on in the talk right before me, we start with functional safety and see how we can map functional safety by picking components and stitching systems together. So it's kind of the opposite direction that we're implementing functional safety. Security, same thing. There's a Google presentation some years old where they announced that all the data at rest, all the data in flight will be encrypted or has been encrypted. The car industry is going exactly the same route. Earlier this year, BMW announced at the Automotive Ethernet conference in Munich that they will be deploying MEC layer security as a de facto standard for every in-vehicle network, because one reason, they don't want anybody to tamper with the network, and they don't want anybody to siphon off data off the network. Okay, so that's key. So that's pretty much the same. Timing behavior, there's some subtleties, some differences, but fundamentally what is called tail end latency or low tail end latency and avoiding congestion in data centers, we see quite some similarities. However, in automotive networks, we need to have very rigid, deterministic low latency. We need to have real-timeness because we're stitching together real-time functionality, control functionality, and put it together in a distributed system. Environmental, that's the cool thing, being a data center guy. I mean, like, there's no shake, rattle, and roll other than an earthquake, I suppose. In a car, this is horrible. Heat waves, temperature cycles, shock, all these kind of things cause quite some trouble. Humidity causes a lot of trouble, in particular in the connectors. So spitting on a fiber optic transceiver is definitely not an option when you're driving a car, right? So definitely that is a challenge, and that is driving the cost for some of the standards, and that is currently the thing where the automotive industry is taking their own routes, where they may use Ethernet as a de facto standard, but they're using different PHYs because they need to deal with different environmental challenges. So the number of systems, that's where things get different, right? In a data center, you have hundreds of thousands of nodes within a modern data center. In a car, the way we see this, probably have less than 10 nodes. There are some OEMs who say, yes, we need 16 because of the luxuriness of our cars, and other guys says, no, cost-driven, it's going to be 3, that's enough redundancy, blah, blah, blah. But if you start thinking about this, it's not just about the individual vehicle anymore, but it's about networks of individual vehicles. And all of a sudden, you start having the same number of nodes, just not within one car, but within a fleet of cars, okay? And that probably across vendors. That's driving this. So the flexibility needs that we see is in modern data center world, a lot of ability is required for dealing with the different workloads. Multi-tenant are driving this in the cloud. And we need screwless driver or screw driverless ways to add and change and remove, replace hardware. In the automotive, a screwdriver is okay, because normally a shop is taking care of that. But what we're also seeing is that with a need for advanced driver assist systems, automated/autonomous driving, we need to upgrade existing vehicles gently by adding more compute power or different compute power. And that means we need some forms of field upgradability by kind of replacing components. And that's what we kind of borrow. That's by no way any advertisement for whatever this company was pushing for that. But what we do see is that the automotive industry, because of their specific needs driven by the cost of the wiring, right, is most likely not going through the kind of the trajectory that we may have seen in data centers from traditional to hyperconverged to maybe composable. Right? But the car industry is definitely very much pressured to jump and leapfrog directly into composable infrastructure, okay, with multi-vendors, interoperability, and it's going to face the same challenges that we see in the data center, because all the functionality in a car will be software-driven. It's not mechanics anymore, right? It'll be software-driven. And software running on composable infrastructure, that's what we start seeing as a push for change in different architectures. There are other industries which face similar challenges. The aerospace defense industry, for example, they face similar challenges where they need, over the life cycle, they need to have field upgradability, replacement of components. And one of the industry kind of solutions for that is what they call the Sensor Open Systems Architecture, or SOSA. That bears a lot of similarity because it uses PCI Express / NVMe Express, okay, as the storage and connectivity fabric for low latency and high bandwidth, as well as Ethernet, and in particular TSN Ethernet, in order to connect systems of systems together. So why PCI Express? okay? And this is not a PCI Express show or something. And you can spare most of the bullets. There's one reason the automotive industry is aggressively pushing for PCI Express, because they're looking for a way to commoditize silicon. The COVID crisis has taught the automotive industry, in particular US and Europe, that dependence on one silicon vendor who cannot deliver is killing their business. I think Ford lost like billions of revenue because they couldn't ship an F-150 truck because parts were missing, right? So the idea behind PCI Express is commoditize silicon, so an NXP and a Qualcomm and an AMD and an Intel, they all become interchangeable because two things are the same: the electrical standard, PCI Express, and the software API, which is a PCI Express framework, okay, become interchangeable. And that is really the push for PCI Express in the automotive industry and similar industries. So why Ethernet? So Ethernet is ubiquitous, right? Ethernet is proven to be pretty resilient against EMI. In an automotive, we do have problems with EMI, but unlike in a data center where things may be more statistic, in a car, if we do have an EMI problem, it's bursting. That means we're parked at the wrong spot, and for a second or two or three, something blasts into the in-vehicle network, and we need to deal with this, right? And Ethernet is pretty good because originally it was invented to put cables into elevator shafts, right? Which is a very aggressive or very hostile environment for EMI from EMI perspectives. The other aspect is there's a clear roadmap to go to hundreds of gigabits in terms of bandwidth. And as you tailgate this industry, you basically reap the benefits. You don't have to reinvent the wheel. You can build on standards that other people have explored and which are quite mature, and you just reap the benefits of this one. That's why we see Ethernet. Why TSN? So TSN's background was from the audio video broadcasting group inside the Ethernet, IEEE, when they started to see that streaming audio video, which is to some degree latency sensitive, right? We notice when the image got flickery because of a buffering event. Okay, so when audio video hit Ethernet, the Ethernet Alliance and the IEEE said this is not good. Okay, it wasn't really meant for that. So they started to develop concepts and a set of standards for dealing with constant streaming under timing issues. And that eventually evolved in 2012 into the TSN task group. TSN stands for Time Sensitive Networking, right, inside the Ethernet. Now, today, TSN is not a standard. TSN is a whole standard soup on top of IEEE standards. I'll go into those ones. But what TSN Ethernet really gives you is two things. Number one is you have a network-wide time synchronization. So if you're running a distributed system, you need to time synchronize. My watch needs to be exactly like his watch, needs to be like his watch, or we can't exchange data. And TSN Ethernet takes care of that form of time synchronization. It needs to be deterministic. Okay, it doesn't help me if on 99 times I hit my brake, it responds right there, and the one time it's minutes later. Okay, it needs to be deterministic, it needs to be predictable up to the way where we have compliance enforcing certain determinism. All right, low latency. Systems need to be responsive. Low latency comes with all kinds of aspects of prioritizing things over not so important things. That gives us a low latency, or what we call a low latency and the worst case execution time of a software system, right? And low jitter, right? If you have a distributed system, even though it's not 99 control units anymore, but it's like 4 or 5, and you try to synchronize these things because you implement software functionality which runs on a distributed system under time pressure. Think about the emergency brakes, right? You need to have low jitter. And the cool thing about TSN is because it sits on top of Ethernet, it has scalable speed. right? So it's a set of standards. Here's some examples of the many standards that are employed and which are kind of fluid. The time synchronization, the standard sits on top of 802.1as, which is a profile of the IEEE 1588 for time synchronization, the good old White Rabbit or PTP version 2, for example, right? We have standards for what we call bounded low latency, like 802.1q, AV, and so forth. It's a whole standard soup if you look at this, right? We have high availability, reliability, where we can now do packet replication and elimination, which is quite similar to what we call multipath routing, sending the same packet, kind of clones over multiple routes. Okay, that's part of the Ethernet standard right now, or TSN standard, and we have resources and profiles and administration. So the whole management layer on top of running a distributed system is right there, right? So a plethora of profiles. Again, we came from audio-video broadcasting, so there's a profile for that. Fronthaul, which is the way to connect antennas to a mobile internet these days. Industrial automation. There's a soup of connectivity standards there, Profibus, Sercos, and so forth, but they're heavily pushing towards TSN Ethernet these days. There's a profile for automotive, in-vehicle, and so forth, right? I do have some backup slides, and I think they made it onto the slides which can online if you want to look deeper into the TSN profiles. One of the things that we like about TSN is it's really orthogonal to all the other protocols you run on top. And so you can get a certain timing awareness, you can do time synchronization without changing so much. So it's kind of like an additional screw you put in and you can mount something on it. So word about technology from Fraunhofer. So Fraunhofer IPMS is one of the 60-something institutes. Think of an institute at Fraunhofer as a separate business unit. And what they basically do is they implement technology and then they ship and deliver it in form of so-called IP cores that you can integrate into your ASIC, into your FPGA. And they have, from the TSN perspective, they have a TSN endpoint. They have a switched endpoint. In TSN, as you can see, you can build daisy chains. That comes from the industrial background. They have switches. They have CAN and LIN and other IP cores. But what we really like about Fraunhofer is they're real good engineers, right? So when you buy something in this modern world, you get a data sheet. Okay, and sometimes the data sheet is rather sketchy. So when we started to source TSN from Fraunhofer, we asked them about latency. We wanted very deterministic latency for on-chip implementations, right? And said, well, we did that. They put oscilloscopes in there and they measured it and they make it reproducible. So we were able to reproduce exactly their data because they're engineers, right? Fraunhofer has hardly any marketeers. That's the good news. So the data you get is hardcore engineering level data. And in this case, it's quite impressive because what they managed to do is they managed to have a very low latency stream interface for an on-chip network to the PHY and from the PHY onto the on-chip network. Okay, and obviously because of buffering happens, it's not symmetrical whether you stream in or you stream out. Okay, the data sheets on all this data. The other thing they did, they were the first who helped us understand the latency of transport within a cable, right? Light isn't really fast if you talk nanoseconds all of a sudden, right? So that's what we like about Fraunhofer IPMS, the guys who are working with us on TSN Ethernet. So where are the challenges now for making TSN Ethernet applicable for multi-gigabit speeds, right? So TSN, the way it has been designed and mostly available from AMD Xilinx, Intel, Microchip, and the likes, okay, Marvell probably has a TSN chip as well, designed for less than 1 gigabits, where application is really in industrial networks, which are transporting limited amounts of data within the system. It's mostly control data. It's software-rich systems running real-time operating systems. And the key thing is the CPUs are fast enough to do all the processing, right? And that's why in a TSN system for 1 gigabit or less, we have DMAs as interfaces into software. Now, if we look at multi-gigabit deployments, things get different. First of all, we have high-performance distributed systems and vehicles and industries, right? A high-speed full HD camera at 60 frames a second is already giving you data at higher than 1 gigabit a system. If you remember some of those cars, they have 17, they have umpteen of those cameras at high resolution and at higher frame rates. So there's a monster amount of data hitting the system. Second thing is the CPUs are getting too slow in order to do the data processing, right? We have to do what we call stream processing or domain-specific architectures with fixed function and programmable function accelerators, okay? And that means a DMA into software is absolutely the wrong thing. And that's why we're working with Fraunhofer to get on-chip stream interfaces between the TSN blocks and the subsequent pre- or post-processing blocks which are sitting inside the chip. And that's the fundamental difference between TSN at lower speeds and TSN at higher speeds like 10 gigabits or faster. So why do we do TCP? Okay, so TCP, I asked some questions because sometimes we like TCP and sometimes we don't like TCP. So we use TCP in an awkward fashion. We use it solely as a transport layer between points. We like it because it has this built-in reliability, right? If you're trying to build a reliable transport against burst networks or networks which are exposed to burst EMI, where at PHY level you can only do so much, and at packet CRC level you can only do so much, you need something at a higher transport level, okay? And when we're transporting PCI Express doesn't like the idea of transaction layer packets being lost. That's when the PCI Express connection goes bust, right? So we need something really dependable, reliable. It's a well understood API, and if you hire a young engineer out of school, he learned about TCP, he probably had a whole semester course about how to program sockets, okay? That's the good news. The other thing is, we are in the luxury of sourcing another technology from another Fraunhofer institute, which is really a full accelerator for TCP IP. That means there's no software, no CPU involved. And if you look at the determinism, it's kind of hard to see here. It really scales with a number of bytes it transports. And the reason you see two little waves there, the two bars in the heat chart, is because of clock domain crossings in a digital circuit. That's the only non-determinism we see. And just for reference, I put the piece, this was measurements they took with the PCI Express card, so I took the PCI Express offset in there, so you see it's pretty low latency. And that's why, by the way, this technology rippled through a bunch of banks in connecting banking systems reliably at reasonably low latency, and I think the entire UK banking system these days licensed the technology from Fraunhofer to run the banking infrastructure. So how do we converge that yet? Okay, so the convergence we foresee is not so much driven by software. Again, we can't afford to have software drive data rates of 10 gigabits or faster. We need to have on-chip systems for that, digital circuits, okay? So the convergence we see is basically twofold. Number one is we need to connect CPUs with CPUs. PCI Express wasn't really meant for that. There was an old concept called non-transparent bridging, and the PCI ZIG, with a little bit of help from Missing Link Electronics, are looking at standards for what is now or maybe called inter-systems bridge. But this is the first form of convergence. And that means not only directly through one PCI Express link to another PCI Express link on the same motherboard, but possibly across a vehicle network. And that's kind of the long-range technology that we're bringing into play here, right? Where we transport PCI Express over TSN or NVMe over TSN at line rates of 10, 25, 50, and we have a lab system now running at close to 100 gigabit line rates, right? So that's the convergence where we see PCI Express and NVMe Express converging with TSN. So the way we implemented this is as a chip, as a digital circuit, okay? So no software involved. And the idea is also to be capable of transporting pretty much any packet-based protocol. PCI Express is not the only one that car guys want to run, right? They have VPCSI2, which is the mobile phone standard for cameras. Lots of cameras enter the car and they need to be transported over this in-vehicle network. So we can take care of VPCSI. A lot of these things are still CAN-based. CAN is controller area network. That's a good old car standard. Goes up to like 1 or 2 megabits, depending on what you're doing here. LIN is an even cheaper standard, but they're all packet-based, okay? And they want to transport that. What we ultimately do is, well, even Ethernet, right? There's Ethernet, there's specific standards, 1TS for Automotive Ethernet. It's packets. So what we do is we have a packetizer that takes the packets from one protocol, terminates it at this particular point, tunnels it across a TSN line at pretty high line rate, and then depackets it. And overall, if you look at this from a PCI Express perspective, this is nothing but a switch. So it's a fully transparent thing, okay? And despite the fact that this beast in between runs Ethernet, possibly with MACsec, TSN, TCP, there's no TCP, no TSN really visible on the outside here. To them, it's just a long wire which meets a certain timing behavior and eventually gets tunneled over this converging network. So this is kind of a look at a system stack, right? So the lower portion is a piece of a digital circuitry, right? Where at the bottom we have a PCSPMA layer to the Ethernet backbone cable. We're agnostic to basically what PHY level we work because every car guy has its own idea. Some believe Ethernet is good enough, some don't think so, and they invent other PHYs. We can put MACsec on top of that. That's optional, obviously. We can put TSN in there. That's optional. For cars, obviously, you need the real-time behavior. We put a TCP IP stack just as a transport protocol, just as another layer of reliability, some in-circuit connectivity, and then we can go all the way up to what we call PCI Express, whether it's PCI Express NTB for connecting CPUs to CPUs, whether it's PCI Express over TSN just to expose devices, or whether we do NVMe acceleration in order to directly talk to NVMe drives. And on top of that sits the software, the operating system software, which in the automotive world is pretty much AUTOSAR OS, classic, or in this case, there's flavors of Linux in there, and that sits the apps. Okay, that's kind of an example of such a system stack. And the way we implement this is, the idea is that anything that's physically directly connected here, as if you would plug in a PCI Express card, an NVMe drive into your box, has exactly the same look and feel as if it was connected far away. That's the idea, because otherwise you would end up changing the software device driver ecosystem, which is literally impossible. So just a quick one on how we do this for PCI Express and NVMe Express. So again, left-hand side, a PCI Express switch. What did we do? We chopped the switch up. There's an upstream switch port, PCI Express spec, downstream switch port according to the PCI Express spec, and we stitch it back together with TSN, multi-gigabit TSN, right? And that way it's a distributed switch, and the root complex or the CPU does the enumeration through the switch and sees every single device as if they would be locally connected. The way we do this in terms of implementation details, this is kind of an FPGA prototype that we did some years ago. We take the packets, the PCI Express packets, strip the physical layer, strip the data link layer, so we end up with a transaction layer packets of PCI Express. And then we transport those transaction layer packets over TCP. We envelope them in a TCP, and we send them out over Ethernet/TSN, right? And obviously there's some magic happening because not all packets should be sent out right away, because sometimes the protocol overhead matters, and especially certain just data bytes, you want to agglomerate them, cluster them, aggregate them, okay? And some others which are highly latency driven, you want to send them out right away. And there's obviously some more smartness in there because in TSN, we can deal with priority queues, different priority queues. So if you have a non-maskable interrupt in PCI Express, MSI, MSIX, for example, that should go probably through a higher priority than if it's just some read or write data to and from a map, for example, okay? And again, while there is TCP and Ethernet and TSN in the middle, this thing thinks it's a PCI Express, so it can behave like any endpoint. And the opposite end is a PCI Express root or CPU, and it thinks like the device is just locally attached to it. And that way we can achieve software compatibility. Here's an example of what we use for testing and validating the software stack. Interoperability obviously is very important here. So this is a setup where we have we call it HPCs. That's a car industry, or some car industries call it the high performance computer. It's just any PC, right? We have a PCI Express connection to a first zonal gateway. Then we have a TSN connection to any other gateway, a zonal gateway, and that has physical PCI Express connectivity then to, in this case, storage devices. The picture here is a system which is an ASIC prototyping system, in this case from Mentor Graphics, now Siemens, which is basically a big Lego thing for us, where we can plug lots of different connectors so we can test for different Ethernet speeds and so forth. And the big silvery cable obviously goes into some kind of a mini ITX PC, because that's our PCI Express connectivity, at least in this setup. So this is how it looks like. Okay, so we connected an SSD in here. Okay, this is a Linux box in our case, and we did a Linux LS PCI, which shows you the PCI Express topology here. And what you do see is, you see the first gateway, and this is for a Xilinx FPGA prototypical implementation. You see the upstream port here, you see the downstream port here, and you see the device. So it's fully transparent that there is an NVMe device connected to the host PC, despite the fact, in this case, there's a TSN connection in between here, right? And because my team is crazy and we have an office in Germany, they tried that over the internet, and it was actually working, okay? So that tells you, doesn't matter what this works. We have timing constraints here. We have timing constraints here according to PCI Express spec. In between here, it's a transparent tunnel, right? And that way we achieve software compatibility. Quick word about PCI Express non-transparent bridging. That's kind of the age-old idea of PCI Express non-transparent bridging. The idea was to hook up multiple processors through PCI Express backplanes. What we basically did, we borrowed heavily from the NVMe spec, which had a different concept, and which favored write-only communication, because writing in PCI Express is just a posted write. You don't have to wait for response. And we implemented an NVMe-style communication for non-transparent bridging, where we have doorbells, and if one CPU wants to read from the other, it writes into this doorbell, and then basically the sender writes the data back into main memory. So it's a flavor of remote DMA, but it's all directly through PCI Express. And we can do that because it's PCI Express, it's transaction layer packets. We can do this over direct PCI Express link, or we can do this over our long-range convergence of PCI Express over TSN. This is how it looks like, okay? Kind of the same picture on the left-hand side, but we have two x86 PCs here connected via PCI Express to separate gateways, and then the gateways are connected via our converged TSN. And if you look at this, you do an LSPCI on this one box, you basically see a non-transparent bridge. It's non-transparent, right? You don't see the PCI Express hierarchy. And on the other side, you basically see this one. And what we basically did is there was a ton of software available in open source Linux, which exposed the good old NTB as a TCP IP socket, right? Everybody knows how to program this. We can basically build on top of that, and all of a sudden we have a TCP IP look and feel API for a non-transparent bridge between multiple CPUs. So, kind of to conclude what we've done, right? We did a PCI Express long-range tunnel, and we start seeing this more as a foundation technology for many different applications. Today, this was more shedding some light of how the automotive industry is finally changing wire harnesses towards more zonal, proximity-driven architectures. We have applications in the field for telecommunications, test and measurement. There's a standard called PXI for these test and measurement cards, which is PCI Express based. And sometimes the sensors are in the basement of a building where no human ever wants to sit. But the test and measurement device, which gets the sensor data, is somewhere else. And they use their own LAN, 10 gigabit fiber LAN, to get into the basement, and they tunnel PCI Express. Right? We see applications again in aerospace and defense. SOSA is one of the applications that we are working with a first customer in the US. And maybe it has applications for data center, because TCP is good if you take the software away. The blur and the load of TCP that it costs when it's run on CPUs is significant, right? So that's why we're basically also looking at other applications. And we recently had a discussion with John Osterhout, who coined this paper. We need a replacement for TCP in the data center. And we're quite curious on how this goes and what his motives were. Anybody interested, go read that paper. It's quite interesting, because what they basically propose is change from a stream-based protocol, which has its pros and cons, over to a message-based protocol, which we like as building distributed systems, right? It's all message-based these days. And particularly, lots of short messages. And this Homer, that's his working title of his new protocol stack, that seems to be nicely positioned for that. That was from my end. Any questions?
I was just wondering if the SSDs ever give you any.
The question is whether the SSDs are giving us any jitter. Please help me understand jitter.
You're talking about deterministic response time. SSDs are pretty famous for not having deterministic response time.
From that perspective, yes. So SSDs, depending on where you're buying from and what firmware version you're getting, they can be quite hard to manage in such a deterministic environment. The overall transport layer in between, it's just agnostic to this. So yes, so we see huge differences with SSD vendors and SSD devices and firmwares in particular, where sometimes where we try to record data and then stream it back, there's a huge gap, right? And that definitely is a problem. That's why we were quite interesting to learn that at least Kioxia, hopefully others, are pushing for this SEF, which may give us a little bit more control over what the SSD, what the flash does in terms of working with us. So the question is, do we face packet loss in a tightly controlled environment? And yes, we do. So again, from an EMI perspective, some of the applications are in quite hostile environments. So we deal with outer space and aerospace problems where packet loss is not driven by congestion buffer loss within switches, but by single event upsets in silicon.
So in that event, TCP reliability is garnered through zeroing in on a subset of missing packets and saying, please send these over again. What does that do to the time-sensitive? I mean, in a normal network, it shouldn't.
Absolutely correct. So the idea is to have a whole layer. So the question is, how do we get reliability just from TCP? And we don't. So we rely, firsthand, we rely on the PHY level Ethernet, the MAC, for sending data in and out. On top of that, we rely on 802.1cb, which is frame duplication and elimination for sending the frame multiple times. In most modern car networks, we're looking at topologies which have some form of redundance, like a square, like a circle, like a token, okay, where you have some form of redundance where you can send the data this way or you can send it this way. So that's the second layer of reliability that we look at. If this is not working, then we rely on TCP because at least a retransmit must happen. Then obviously the determinism is gone, but at least we didn't lose the functionality.
Have you instrumented the number of times when TCP reliability algorithms come into play? Is it actually helping?
So the question was, how did we measure when TCP as kind of the last resort of reliability kicked in? And yes, we did. So in the discussion with car guys, if you spend like, I don't know, 1 million transistors on a chip for this extra level of security, they negotiate you down for getting rid of it, right? Because it's cost driven. And we've seen burstiness in the lab and actually out there in the field where none of the other layers actually could protect, but we didn't want to lose the connection, and that's when TCP kicked in. And that's when we literally saw a retransmit at TCP layer.
Briefly mentioned CXL earlier in your talk, but then really mentioned it any further. Anything about where that's going?
Well, we're observers, so the question is our relationship with CXL. So we like CXL, and one of the things that we did a lot of heterogeneous compute systems where we put FPGAs and GPUs and Power 9 systems together for certain IBM applications. We like heterogeneity. What we didn't want to do is being like a 30 headcount company being in this fabric war. Right? That's why we were quite happy that the C6 and the OpenCAPI and I forgot the Gen Z, right? That they all kind of decided to converge into CXL. So we're a bystander, we're watching it closely. We do like the idea of cache coherency that we basically got used to in CAPI/OpenCAPI, the IBM invention. The technology that we're building is agnostic to CXL, so if there would be CXL functionality, it'll be transported just by PCI Express. And what we are actually looking for in some of those applications is augmenting memory, RAM, with flash as persistent memory in case we need to do things like swapping a system. Right? In some of the applications, it's very difficult for us/our customers to figure out how much RAM do you need for this particular algorithm, like this sensing algorithm, right? So yes, we're watching CXL, and we're hoping that more of the systems start using CXL 3.0 in particular, because that's when we see some of those functionalities kicking in. All right. Thanks for your attention.